Alright, silly people, here's the situation. We've got these two matrices, and first of all, we're going to see whether or not they are diagonalizable. That's easy to call, since both of these matrices are Hermitian. That is, that if you take the um, Hermitian adjoint of either one of these, you'll just get back out the matrix that you started with, um, because both of these matrices are real, so all you're really doing is taking the transpose of either one. Uh, and all Hermitian matrices are diagonalizable, so we have that going for us. Um, do they commute is the next thing that we're going to check. So um, that is the commutator of A with B equal to 0? So let's just do the commutator of A with B, which is AB minus BA. 1, 4, 1, 4, minus 2, 4, 1, 4, 1 here. And then B was 1 minus 2 minus 1 minus 2, 2 minus 2, minus 1 minus 2, or positive 1 on the bottom right element there. And then that's all going to be subtracted by b times a, which is going to be 1 minus 2 minus 1 minus 2, 2 minus 2 minus 1, 2, 1 times 1, 4, 1, 4 minus 2, 4, 1, 4, 1. Right? So that's a terrible equal sign. But multiplying these matrices together, we have 1 minus 8 minus 1, and then 4 plus 4 minus 4, and then 1 minus 8 minus 1, and then minus 2 plus 8 minus 2, and then minus 8 minus 4 minus 8, and then minus 2 plus 8 minus 2, and then over here minus 1 plus, or minus 1 minus 8 plus 1. It's minus 4 plus 4 plus 4, and then minus 1 minus 8 plus 1. That's the first couple of matrices done, and then the other couple looks like 1 minus 8 minus 1. No. There's supposed to be a minus sign right there. My bad. But then, yeah, so that's minus 2 minus 8 minus 2. And it's actually, yeah, minus 2 plus 8 minus 2 for sure. And then minus 1 minus 8 plus 1. That's cool stuff there. And then this is going to be 4 plus 4 minus 4, and then minus 8 minus 4 minus 8, and then minus 4 plus 4 plus 4, and then this is going to be minus 1 minus 8, or actually no, it's going to be 1 minus 8 minus 1, right? Yeah. And then minus 2 plus 8 minus 2, and then minus 1 minus 8 plus 1, right? So yeah, these are the same. 1 cancels out 1, 4 cancels out 4, 1 cancels out 1, and then other stuff happens as well. These are kind of a little bit complicated. but not so much that we'll have to cut it out of the video or anything, because we're just going to do a little bit of simplifying on these, because the first two matrices multiplied together ends up being minus 8, and then 4, and then minus 8, and then that's going to be 8 minus 4, so 4 here. Then it's minus 8 minus 4 minus 8, which turns into minus 20, and then this is 4 here again, minus 8 here, 4 here, minus 8 here, and then the second pair of matrices multiplied together is minus 8, same thing, minus, or it's just 4 here, minus 8, and then 4, and then minus 20, and then certainly that is 4, and then minus 8, then 4, and then minus 8. So yeah, that just gives you 0, so the matrices do in fact commute. But now we get to do the bulk of this problem, which is finding out what the eigenvalues of A are, right? So A, to find the eigenvalues, you just take what we have for A and subtract lambda from the diagonal elements, and take the determinant of that matrix. So we have 1, 4, 1 minus lambda. And then once you have the determinant, you set it equal to 0. So we have 1 minus lambda times minus 2 minus lambda times 1 minus lambda plus 16 plus 16 minus 2 minus lambda minus 16 times 1 minus lambda, and then minus 16 times 1 minus lambda. Yep, that should be everything, and that you set it equal to 0. We're going to group this together in a way that is nicer. Moving the minus sign out of the 2 plus lambda term, and then with a 1 minus lambda squared term left over. Adding up the 16s to make 32. Moving the minus sign through this term here, so it's going to be plus 2 plus lambda, and then grouping up the minus 16 lambda stuff into minus 32 times 1 minus lambda, right? We can expand the 1 minus lambda all squared stuff into 1 minus 2 lambda plus lambda squared. On the outside of those parentheses, we end up having a 34 plus lambda minus 32 plus 32 lambda, right? And then we can multiply those two parentheses terms together to get minus 2 minus lambda minus, or actually plus 4 lambda plus 2 lambda squared minus 2 lambda squared minus lambda cubed. And then on the outside of that, we just do 34 minus 32, which gives you 2. And then 32 lambda plus lambda just gives you 33 lambda, right? So then the minus 2 will cancel out the 2. Minus lambda plus 4 lambda plus 33 lambda turns into 36 lambda. 2 lambda squared cancels out 2 lambda squared, and you have minus lambda cubed equals 0. So we can divide the equation by lambda and just get 36 minus lambda squared equals 0, and that gives you only 2 eigenvalues, which is interesting because it's plus or minus 6, but then the other eigenvalue disappeared because it's a three-dimensional matrix. It's got to have 3 eigenvalues, and so since we can't find it, that means that that eigenvalue is 0, and we are good there. Um, Finally, we need to find the eigenvectors now. So we can set A back up, which is 1, 4, 1, 4 minus 2, 4, 1, 4, 1, and multiply it by some arbitrary eigenvector. I'm going to call the eigenvectors A and B for brevity. Um, so the first eigenvector will then be A1, A2, and A3 for the components. And then on the right-hand side, we'll put the first eigenvalue, which is positive 6. A1, A2, and A3 here. Okay. Just doing the multiplication, we have the equations A1 plus 4A2 plus A3 equals 6A1, 4A1 minus 2A2 plus 4A3 equals 6A2, and A1 plus 4A2 plus A3 equals 6A3. Now check it out, we have these two equations here, the first and the third one, are the same on the left-hand side, so we can say 6A1 equals 6A3, or actually A1 is just equal to A3, so that's pretty cool. And then we can take the third equation then and be like, or the second equation, so it's 4A1 minus 2A2 plus 4A1 equals 6A2. We can add 2 to both sides and add up the A1s on the left-hand side, so we have 8A1 equals 8A2, so you just get A1 equals A2, and that's lovely. Now that we have the relationship between the components, we can set it up so that we have the simplest 3 components being 1 and 1 and 1. It'll have to be multiplied by some normalization constant, which we have to find, which I'm just going to call C for now. So, of course, you just take the dot product of A with itself and set it equal to 1. So we have C squared is 1 plus 1 plus 1 equals 1. So 3C squared equals 1. So C ends up being 1 over square root 3. And so the eigenvector A is going to be 1 over root 3 times 1, 1, 1, right? Then the other eigenvector, which I'm going to call B, you find it by doing the same sort of thing. You take the matrix A, 1, 4, 1, 4 minus 2, 4, 1, 4, 1. Multiply it by B1, B2, B3. And then on the other side, you put the other eigenvalue, which is minus 6. We have B1, B2, B3 here. Doing the matrix multiplication, we have B1 plus 4B2 plus B3 equals minus 6B1. 4B1 minus 2B2 plus 4B3 equals minus 6B2. And B1 plus 4B2 plus B3 equals minus 6B3. Again, the left-hand side of the first and third equation there are the same for either one. So we can set B1 equals B3. And then with the second equation, we can be like 4B1 minus 2B2 plus 4B1 equals minus 6B2. Add 2B2 to both sides. We have 8B1 equals minus 4B2, and then we can divide by minus 4, and we get minus 2B1 equals B2. So the unnormalized eigenvector B just looks like 1 minus 2, 1, with some normalization constant to give it that. So C squared now is going to be 1 plus 4 plus 1. So, and that you don't set it equal to 0, you set it equal to 1. So C is equal to 1 over root 5, and now the normalized B is just not 5, but 6. That's what you want. Yeah, B normalized is 1 over root 6 times 1 minus 2, 1, right? The next thing that Griffiths asks us to do is to check if the eigenvectors that we just found are also eigenvectors of the matrix B. So to do that, all we have to take is the matrix B, which is again this guy, minus 2, minus 1, minus 2, 1. Multiply it by our eigenvectors from before. We're going to do A first, so it's going to be 1 over root 3 times 1, 1, 1. On the right-hand side, we'll have 1 over root 3, some kind of constant, which is going to relate the two, which is actually going to be the eigenvalue. So we're going to call this L1 of B. So 1, 1, 1. Okay, so doing the matrix multiplication and also canceling out the 1 over root 3 thing, we have on the left-hand side 1 minus 2, 1 minus 1 minus 2, 2 minus 2 minus 1 minus 2, 1. Incredibly easy multiplication there. And then on the left-hand side, it's L1 times 1, 1, 1. Just doing the math in there, we got what? Minus 1. We've got minus 2, plus 2. I guess I should have written the plus signs, but it doesn't matter that much. And then these guys cancel out. So we have minus 2, minus 2, minus 2 equals L1 times 1, 1, 1. So it looks like the eigenvalue for B is minus 2. Okay. Going again, we got 1 minus 2 minus 1 minus 2, 2 minus 2 minus 1 minus 2, 1 on the left-hand side, which is going to be multiplying the other eigenvector that we found. So 1 over root 6 times 1 minus 2, 1. And on the right-hand side, some other eigenvalue of B, which I'm going to call L2, divided by the normalization, and then the 1 minus 2, 1 thing. The normalization goes away again, and then this matrix, whenever you multiply it, you get 1 plus 4 minus 1, and then minus 2 minus 4 minus 2, and then minus 1 plus 4, and then plus 1. Neat. On the right-hand side, it's L2 times 1 minus 2, 1. Doing the math in there, 1 minus 1 is 0. And then also 1 minus 1 is 0. So it's 4 minus 8 and 4. And this is L2 times 1 minus 2, 1. Clearly L2 is just 4. No idea if B has another eigenvalue. I didn't check because the diagonalizing B by itself is actually pretty difficult. But yeah, at least they share these eigenvectors. All right.